Hello everyone. So I'll wait for 5 more minutes, and meanwhile, if anybody has any questions, they can ask or write in the chat box. Okay? So maybe I can start now. So hello everyone. Welcome to practice session 4 of Geographic Information System. I am Akansha Kumari and I am a PhD scholar at the University of Queensland and IIT Delhi. So can anybody confirm whether the screen is visible or not? Okay. So, and what about the audio? Now is it okay? Anybody confirm? Okay. Uh, what about now? Like, what is the issue? Can everyone increase their sound and then confirm whether the audio, so I'm audible or not? Okay, okay. So I hope, okay, okay. So I hope now it's better. So we'll start now. So if anybody has doubts, they can ask now or during the session and at the end of the session. So if there are any doubts, you can ask now or I'll start. Any doubts? Okay. So, so my presentation is not moving. Okay. So in this course, we are studying about geographical information system. So you all know, like we have completed about 3 sessions, and you know what is geographic information system and why it is important. So it is basically why we do this. We basically try to uh, get information about the real world by making a simple layer of the real world. So this GIS layer is simplified layer of the real world, and it contains the information that we are interested in. So if you are interested in floodplains, then from the real world we will extract the information about the floodplains. So this you already know, and in the last class we talked about how, like, we did some hands-on practice on how we can create vector data layers from an image. So first you have to do georeference this, and then you can make shape files using, like, you can make point shape files, polygon shape files. So different kinds of vector shape files can be done by digitizing. So digitizing is basically manually tracing the map to get a vector data. Okay, so this is what we did, and these are the steps. So if you want to do it on your own, you can follow these steps to make a shapefile. Okay, so and these are the steps like which I have told you can use to do georeferencing. Okay, so for QGIS, and this is for ArcGIS. So in the last class we focused on the vector data model, and in this class our focus is going to be raster data models. Okay, so before that I want to ask how many of you have downloaded QGIS? So, or ArcGIS. So just type if you have downloaded QGIS or ArcGIS or none. Okay, QGIS. What about others? Okay, QGIS. Anybody with ArcGIS also? No one? So only 2 people. Okay. So if you have downloaded, what you can do, you can try doing georeferencing steps. So that does not need any like large data or downloading any data. You can just take any map which has grids or some cities or something that you want to extract, and then you can just try go to QGIS and follow the steps that we followed in the last class. Okay, so anybody tried the georeferencing steps or digitization steps? Because it will be good if you by yourself try those steps, and then if you have any doubts, ask me. Okay, so for the raster data, what I'll do, we will, okay, share the map. So today I have shared one map. Uh, you can just Google any map. Like you don't need to use the same map as I did. Just Google any map which has grids or something that you can use as a reference point. Like at least 4 points should be there to for you to do georeferencing. Okay. So so that is why I didn't share any map, because like you can just Google and it's up to you. And if you use another map, then you can understand like what is the thing that is needed for georeferencing. Like you need at least 4 points that you know, like the lat long of those points you should know. Okay, so just try it on your own, and like somebody already tried and they have no problems, so that is good. And other people they also try, and if they have any problems just tell me. Okay, so it will be good if you learn those. Like I already know, but if I'm teaching you, you should all also know all those steps. Okay, so let's move on to raster data. So for raster data, what I will do, I will download digital elevation data, and that data is continuous. You can see this is continuous phenomena. So that is basically a raster data type, and we can see like what are the different features of the raster data model, how can we analyze slope. So these things we can do with that data. So I'll first talk about the raster data, all the theories, and then we will move on to the elevation data part. How can you download, what are the different ways of downloading, how can you make a map out of it. So those things I'll teach you today. Okay, so let's start. So as you already know what is raster data, so in raster data, space is divided in different grids, uh, by different grids, and that makes different rows and columns, and each cell has one value, and one cell is called as pixel. So the smallest unit of the raster data is called as pixel, and it is suitable for continuous phenomena, so like elevation, temperature, rainfall data. So these things can be represented by raster data. Okay, so this is how raster data looks, and this is different uh, land use uh, land use classification, land cover classifications. So you can see there are different cultivated area, forest area, and how they are divided, that also we will like later on in the classes we will see how can we make our own land use land cover maps. Okay, so those things we will be doing, but not in today's class. Okay, so now how it looks. So suppose this is the real world feature. Okay, and this is your raster data. Okay, so what happens in raster data, you divide the space into like you make these grids, and then we have multiple rows and columns, and at each grid we have one value. So this is how raster data will look if the real features are like this. And if you look at the vector data, So vector data is defined by pair of flat long values, so pair of xy coordinates. Okay, so for this, for showing this square, we will use these four pairs of coordinates. Okay, so this is the difference between raster and vector data. And in raster data, the smallest unit is pixel. So suppose you downloaded any satellite data like Landsat image, and if you zoom in, you will see these kind of pixels, and you can see these pixels are uh, they have something called as digital number. So digital number basically depends on the intensity of photon that is going to that particular detector, corresponding detector. Okay, so if the intensity is very high, the value is going to be very high and it will appear more brighter. And if the reflectance, so this intensity will depend on the reflectance of that particular, so suppose this is a blue band, so for blue light what is the reflectance, so if it is getting reflected heavily by something that is there, then the values are going to be high. If that is getting absorbed on the ground, or it is not getting much reflected, then the values are going to be less, so it will appear darker, and with high reflectance it will appear brighter. Okay, so this is what these numbers means. And there are different things that you should know. First is resolution. So resolution is the smallest unit, so we talked about this. So so can anyone tell what is the resolution of Lancet image typically? Anyone? Okay, so whenever you download the data, so suppose this is the ground for which this image has been taken. So, so this particular area for which the one pixel is going to be corresponding to some area on land, right? So that particular area is will define the resolution. So what is the geographical space or uh, geographical area that is covered by the smallest unit? So for Lancet, it is typically 30 by 30 meters. So 30 meters by 30 meter, 30 into 30. So that 30-meter is the resolution, spatial resolution of the Landsat data. So if the cell dimensions are small, so suppose there is one satellite which is, so yeah, it was 30 meters. And the ratio that you have given is called as scale. So that is not resolution, that is scale. So that also is kind of showing that this particular one unit correspond to this much area. So that scale is, I think, different. I'll look into it. So resolution is defined in meters or kilometers, and for Landsat it is 30 meters. But different Lancet, recent ones, can have like higher resolution. So whenever you download the data, you should always look for the resolution that the image is giving. Okay. Now next is zone. So zone is the location that have similar characteristics or same values, and value is like each pixel will be having one value. So for representing any continuous information, each pixel is going to have one value. Okay, and location is ordered pair of lat long values uh, that particular space is taking, and then pixel values or dn values depends on what, the reflectance. So uh, the gray level, so if it is 8-bit image, it will cover from 0 to 255 dn values. Okay, now there is one question: which data model divides space into rows and columns, storing one value per cell? Vector, raster, tin, and topographical. So it is pretty easy. It is raster model, and it's uh, raster grid store continuous values per cell. Okay. So this raster data model is suitable for storing temperature variation, plotting bus routes, representing political boundaries, or drawing subway lines. So it is storing temperature variation, and all the other ones are uh, represented by vector data models. Okay. Now this I have told so many times. So what is the smallest mapping unit in raster data called? So it is pixel. Okay. Now this is calculation. So suppose the raster cell is 30 by 30 meter. So what will be the area of 50 cells? How are you going to calculate? You just have to multiply by 50. So 50 into 30 into 30. So that will be 4500. Yeah, correct. Okay. Now, how can you represent raster data? So there is one type which is called as quadtree representation. So suppose there are different types of land use land cover types. So A, B, C, D. So different types, and you can see we have written rows and columns here. So rows and columns, and you can see A, B, D, and C is written here. Now in land use map, you can show it like this. So this is a real world, but since in the raster representation you can only use squares and rectangles. So squares, basically the smallest units are squares. So your representation is in raster data is not actually going to match with the real world, but it can roughly follow it. Okay. So suppose this is land use map, this is industrial area, this is rural area, then residential unit is also divided into different things. And then in quadtree representation, how you can show it? So all these four quadrants can be represented by 0, 1, 2, and 3, and then if you further divide it, it will be 2 0 2 2 2 3 2 1, right? 2 0 2 1 2 2 2 3, and if you once again divide it, it will be 2 1 0 2 2 1 1 2 1 2 and 2 1 3. Okay, so this is how you represent in quadtree representation. Okay, and in semantic representation it will be like this. So root is from the root to leaf. So it will be 0, 1, 2, 3. Then from leaf to nodes, it will be 2, 0, 2, 1, 2, 2. Then again, it will again divide. Okay. So if you make a table of attributes out of this, it will look something like this. So you will write all the quadrille levels. So 0 is industrial area, 1 is also industrial area. Now if you move on to 2, 2 was what? 2 was residential area, right? And then if we move on to 2, 0, then in the residential it is divided. Okay. So this is how you can make a table of attribute for a quadrille representation. Okay. So now quadrille model is a data compression method for raster data, and it recursively subdivide homogeneous area into larger cells. Okay. So what are the pros? It is very fast and compact storage, and the one thing is it is less suitable for heterogeneous data, and processing time is large. Okay, so this is one type of compression method for raster data. Yeah. Now we will move on to different raster operations that we have. So So each integer value is associated. So what you can do, you can change the symbology of the uh, figure. So you can see different colors are representing different values. Okay. So these are the different ways. You can also make contours. So that also we will see. So from the EM data, contours are basically an imaginary line. So they are not real lines in the world. They are imaginary lines that and one contour will represent the line, and that line will be having same value at every place. Okay. So these contours, so they pass through pixels which have constant values. Okay. Sequence of colors also can be used, and this is like uh, you can contours can be seen. This is a 3D map, so that also can be made. Now another question. So quadri model is used to what? Improve network analysis. B. Compress raster data. C. Vectorize polygon data. And D. Store topology. Yeah. So it is B. Compress raster data. So this is done to like compress the data, and now converting a reverse shapefile into cell-based format is called what? So rasterization, vectorization, quadri subdivision, or topology generation. Okay, so reverse shapefile is what? A vector data, and cell-based format is a raster data model. So you are converting a vector data into raster data. So that is going to be rasterization. So you guys are correct. It is rasterization. So grid model. So this is another model. So it has regularly spaced elevation point in matrix. So suppose uh, uh, at sorry use a pen. So in this, what happens? At a regular interval, you will have some values. Okay. So suppose, so at every regular interval, you will have one elevation point. Okay. So this is very simple, easy to relate to raster data, but this is very poor to represent any linear feature. So you don't have any value in between these 2 points. So you will lose how this is changing. Okay. So you don't know like whether this is going up or down, how this is changing. Okay. Now we have conversions. So vectorization is raster to vector as the name suggests, and rasterization is vector to raster. Okay. So this is done because like we in different application different formats are preferred. Okay. So that is why we need to convert from one data model to another data model. Okay. So this already we discussed, so I'll not go through it again, but there are some questions. So if you have um, gone through the previous session, you can answer this. So which is not an advantage of vector data? High geometric accuracy, good for network analysis, good for continuous data. Yeah, correct. DTM represents what? Elevation plus building, bare earth elevation, land use category, or what under depth. Terrain model is basically bare earth elevation. And DSM, which is surface model, that contains elevation plus building information also. Okay, the terrain model is only going to represent bare earth elevation. So this difference you should know, and whenever you download elevation data, you should know whether it is terrain model or surface model. Okay, so now we are coming to the elevation data. So for surface representation, we have three different types of models. So one is digital terrain model. So this represent bare earth terrain. Okay, so you can see, suppose this is the real world with trees and houses and grass. So terrain model is going to represent uh, this surface data only. Okay, not surface, only the elevation, terrain elevation. It will not cover the trees or the house. Okay, and the surface model. So digital surface model uh, contains terrain data as well as above ground objects also like building and trees. So if the resolution is very high, then you can get these information very clearly. Otherwise, the particular pixel is going to represent an average value. So mostly if the trees are very rare, it will just represent the terrain only. But if it is very dense, then it will represent basically average tree height. Okay, so this is what surface model is, and then elevation model is like generic term for both surface and terrain models. Okay. So now moving on, what are the so these SRTM, Aster, Equinox, Cartosat, and this GTOPO 30 model is basically commonly used digital elevation model dataset. So now this particular information is for spatial resolution, radiometric resolution is for cartosat data. So in cartosat data, you can get the resolution of spatial resolution of 1 meter to 5 to 30 meters. Okay, 1 meter also, 5 to 30 meters also. And how they are going to get the information about the elevation. So what happens in that those satellites, we have we have uh, two uh, two uh, what is this called? Two cameras. Okay. So two cameras seeing the same site at the same time. So these are called as stereo cameras. Okay. So what they are doing, they are looking at this particular elevation at the same time from a different viewing angles. So if you remember, like in 11th, 12th, or before that also, we learned about paras parallax shift. Okay, so if you close your one eye, so why we are able to see 3D image of this world from our eyes, because we have two eyes. So if you close your one eye, and if you look at your finger, and if you close the other eyes, you are going to see a shift. Okay, so if you like, if you are watching from both of your eyes, then you can see like your uh, finger is going to be fixed. But if you close one eye, and then close that particular eye, and then open another eye, then what will happen? Your image is going to shift, your finger is going to shift. So that error is called as parallax error, so parallax shift. And this is what happens when the two cameras are viewing the same site from two different angles. So from that shift, uh, like the 3D map can be made. So you can see, so this A and this is tree B. So if this camera is viewing this, so this is going to intersect here, and A, and for B it is going to intersect here. So for this particular B, the intersection point is going to be lower than this one, A. So that is why you know that this particular elevation is less than this one. Okay. So we have information about X, Y, and this Z position also. Okay. So that is how we can get elevation data. So we have two cameras looking at the same site from two different viewing angles. So the working principle is same as our eyes. Okay. So I hope this is clear. Now, for downloading the Cartosat DEM data, you have to go to Bhunidhi website. So this is an Indian website, and it has a resolution of 1 meter also, 30 meter also. So the 30 meter is free of cost, and you don't have to pay. But for higher resolution like 1 meter or 2 meter, there is going to be a payment, um, so that is priced product. So what you have to do for downloading it? Yes. So for downloading it, just go through this website. So you can just copy, and you can go to the website. You have to log in, and you need to give information about what is the area that you are interested in. So you can select the area. So it is similar as what we did in uh, while we were interested in downloading the USGS data. So anyway, just zoom in. Okay, and you can select open data. And if you are interested in higher resolution, you can select for price data also. And then go to product and select Carto DEM. Okay, and you can see the free version is this one, Cartoset 1 pan Carto DEM data, 30-meter resolution is there. And then you can submit, and you can see for these grids we have data sets. Okay, so it contains information from for the Indian region. So you can see these are the sites for which we can download the data. So you can add to cart and then download the data. So since I have not logged in, um, I cannot download it now. So you have to log in, make an account, register here, and then you can download. Okay, so this is how you can download the Cartoset DEM data. So I have given the link, and this is how you can download it. Now we'll move on to the next website. So there is SRTM data. So that is also one kind of DM data, and that you can download from USGS website. So I think in the second class or the first class we saw how can we uh, get data from USGS website. So in the last when I was telling about Lancet data, but if you want to download the digital elevation data, you can download from here, digital elevation. So maybe I can show you. So this is USGS Earth Explorer website. And this SRTM data is also 30-meter, 90-meter resolution. So 30-meter is the best that you can get. Okay. Suppose this is the area, we'll go to data set, go to digital elevation, and then go to SRTM, and then first one, SRTM 1 arc second global. Okay, and then go to results. So you can get these data, digital data, and you can download if you log in. Okay, so this is how you can download. Now, if you want to use SRTM data set, then in QGIS, you have the option to directly download from the software itself. Okay, so what I'll do is that I'll show you how can you download uh, directly from there. Okay. So there is one question about the videos. So videos like for the session up to session 3 I have already uploaded, and there is a link, so I'll show you why this is happening. So in the SWAM portal itself, you can see there all the files are there, like all the PPT and also So if this is the website, and if you go to problem solving session, and if you click here, you can see all the videos and presentation is uploaded. Okay, so just go to the website, swam portal, and then go to problem solving session recording. Okay, any doubts? Okay, so now what we will do, we will download the QGIS Open Topography DEM plugin. So what this plugin does is that it can directly download um, the elevation data. So the SRTM data that you can manually download from there, here you can just use the software, go to your area of interest and then download. So you have to go to plugins and then search for Open Topography. So Open Topography DEM downloader. Okay, so you have to install this plugin. So now the plugin has been installed successfully. Now what we have to do, we have to look for the plugin. So if you like, there is an icon that will appear like this, if you see here. So this particular icon is for Open Topography DEM downloader. If you cannot find it, you can also go to plugin and then go to SRTM downloader. Okay, so let's see if we use this. We also have to define the extent for which we need to download the data. So for that, what we will do, we will add one base map. So I'll go to a base map and then zoom into some area which I'm interested in. Okay. So we'll go to some area which is this. Okay. So suppose this is the area of interest that we are interested in, and then we'll go to this. Now here you can use, like, you can download the data from uh, these different DEM data types. Okay, so we can choose SRTM 30 meters, and then for defining the extent we can use current map canvas extent, or you can also give uh, like you can give a layer to define the extent. Okay, and then here you have to provide an open topography access key. Okay, so for this you need to make an account um, to provide API key. Okay, so this access key is needed. So how can you get the access key? So you have to go to this open topography and then make an account and get API access key. So let me show you how can you do that. So for this, you have to just register yourself. You can go to my account in this open topography and then use your email ID. So I have to log in. Uh, Once you log in, you can get your API key. But since I'll not log in right now, but I can just add some screenshot later on. Okay, so the presentation that you will get, I'll add some screenshot how to get API key. Okay, right now I can't remember my password, so I'll not log in right now. Um, so there you can get some API key. So it will look something like this, and you can just copy paste here your API key and then run. So since it is downloading data directly, you cannot download a very large area data sets. Okay, so your data extent should not be very large. Okay, so that is why I zoomed in, and now you can see we have our DEM data. Okay, so these steps you can try and get your elevation data also. Okay, so this is also a topo map, so you can see the elevations, and if you see here, this is this SRTM data is also following that elevation. But right now you can see it is not very clear, right? So what we can do, we can go to properties and then we can go to symbology, and then you can change the symbology. So if you change it to single band pseudo colors, so now you can use these colors to define your topography. Now let it lie. So now you can see these blue bands are showing where the elevation is very high. So these are the points where elevation is high. These are low elevation points. And you can also see this is kind of a river network that is there. So this is how you can change symbology. Okay. Now except for this, you can also make contour lines out of it. Okay. So how can you make contour lines? So you have to go to raster, then analysis. So and you can also calculate slope. So there are lots of things that you can do with the raster data. So you can calculate slope, you can calculate the terrain ruggedness or TPI. So these are the things that you can do. So let us do slope analysis. So now it is automatically taking this. Compute edges also and then run. Okay, so this is strange. I have to see. Okay, so we also have to, so right now we need to change the projection and then only we can do this slope analysis. Okay, so first of all, after getting this data, you have to project it. Okay, so I have given the steps here. You have to project it. So let us go and do that. Projections and then wrap reproject. So now it has been reprojected. And then you can also clip it. So for raster data, you can do clipping um, function also. So this clip function can be done from raster, go to extraction, and then clip raster by extend. So suppose if you are interested in this particular only this data, you can use this extend, this canvas extend to clip the data. So you have to just use um, go to raster, go to extraction, and then clip raster by extend. Okay, so this you can do. Now suppose the whole area is what you are interested in. So for that, what we have to do, go to analysis and then slope. So now we can do slope calculation. Master analysis and then slope. Use represented data and compute. And again the same issue. So no worries. I'll look into it why this is happening, and in the next class I can tell you. Mm, but for this class, what we can do is that we can make contour lines so that we know which are the uh, areas which are equal, kind of equal. Okay, so for that you have to go to raster. So for raster data here in QGIS, you have your raster and vector tools very clearly given. So for raster, these are the analysis that you can do. For vector data, these are the analysis that you can do. Okay, so go to raster extraction, then contour. So we have to decide like what should be the interval between the contour lines. So suppose I give 50. So at every 50 meter, I want one contour line. Okay. So run and then close. And now you can see we have these contour lines on our map. Okay. So at every 50 meters there is one contour line. So there are more contour lines where there is a slope, because here like the elevation is changing very fast, so that is why we have more contour lines. If there is like the contour lines are very far away from each other, that means that particular area, uh, in that particular area the elevation is not changing that much. Okay, so this is how you can interpret the contour lines. Now what you can do, you can change the symbology and also label these lines. So now suppose I use this. or simple blue line. So this is how you can change your type of representation of contour lines. Okay, so now you can see this has been changed. Now if you want to label it, in the properties you have to go to labels. Now once you select single labels here, you can see the value. If value is FID, so this is ID. So if I add this, you can see these are the numbers that are appearing, and your elevation range is starting from 300 to 700, 800. So now you can see these values are not the elevation values, these are the ID that has been assigned to these lines. Okay, so always when you are um, adding label, you have to change this to elevation. Okay, so not FID, not ID, change to elevation. Now we'll apply this and then okay. So now if you see, this is starting from where? Starting from somewhere around 300, 300, 350, 350 because 307 is the minimum value, and then going to 750. Okay, so now these values are correct, these labels are correct. Okay, so while you add your uh, label in the contour lines or like in any uh, vector file, always check whether the label is uh, adding the ID label or the value, elevation value, or the rainfall value. Okay, so these are the things that you should consider while you are doing this contour analysis. So these contours can be made for the rainfall also, for temperature also. For any raster data, you can make contours and see which are the lines that are having equal value. So these lines have equal value, equal elevation value. So that is 500 meters. Okay, this is 750. So I hope this is clear. Everything is clear or not? Any, if you have any doubts, you can ask. So what I'll do, we'll take a 5 minute break, and meanwhile, you can ask me if you have any questions, and then we can start again. Okay? So I hope everything was clear till now. Just message me if it was clear or not. So I also checked, like, the thing that why we are doing this reprojection is that this TM data is usually in geographic coordinate system, and we also talked about projection. So if we project it in a if we project it, then what we are doing, we are converting it into uh, like the units of meters. Okay, so what happens while doing this slope analysis, if the coordinates are in geographic coordinate system, uh, then it can be problematic and your slope values will come uh, wrong. Okay, so always, like, if you have to calculate length, or you have to calculate area of a polygon, or you have to calculate any, like, quantitative estimate, you always have to convert the coordinate system from geographic to the projected one. Okay, now while we were doing this reprojection, if you see this, this was the raw data that we downloaded. So for looking at what is the projection system that it is using, we'll go to properties and then go to source, and then you can see this is WGS EPSG 4326. Okay, so this is a geographic reference system, and you can see it is also written here that we have to change this representation. Okay, we have to reproject it. Okay, so okay, so if you change the coordinate system here, it will not change the reprojection. Okay, so you have to go to processing and then wrap and reproject. Okay, so now see, when we did reprojection, what is the coordinate system? It is again the same. Okay, it is again the geographic coordinate system. So that is why the slope value was same again. Okay, so now what we have to do, we have to change it. We have to sorry, we have to reproject such that the units of the system, coordinate system, is in meters. So this is geographic one, so we have to remove it. First remove this, and now what we will do, uh, we'll go to projection and then wrap reproject, and then we'll add the input layer. So this is this, this was default, this one, and the target should be a coordinate system which has units in meters. So what we'll do, we'll go here. So this, for the target one, we'll so first of all go here and then select predefined CRS, and then here we need projected one, right? So in the projection, go to space is very less for us to see. So you can also search it. So it is not coming up. Okay, so we can manually do it. So go to projected. In Mercator. So now if I select this is what? This, if you see here, the units are in meters. Okay, so we'll choose this and one and then close. And now we should always check. And now it is what? It is a Mercator, pseudo Mercator. So now the units are in meters. Now let's see if we are getting the slope value. So we'll go to slope, compute edges, and then close. And now I'll change the symbology so that we can see the image clearly. And we'll remove this. So you can see the places which were planar areas. So they have a slope value which is close to 0, and as you go like up, so on the heels the slope values are higher. Okay, so this is how you can do the slope analysis. And always check the projection of the reprojected layer, because if it is not projected correctly, then you will not get the correct slope values. Okay, so this is how you can do the slope analysis in QGIS. And I have also given all these steps in ArcGIS, so you can go through this and If you have any doubts, you can ask me. I'll not do this in today's class. We'll move on to the next topic. Okay. So now again for the raster data. So I wanted to show you, like if you zoom in, you can see these pixels. So can you see these pixels? So these are the smallest unit that we were talking about for the raster data, and each pixel is going to have one value. So whatever area, so this what area it is covering? Can anybody tell? This pixel is covering how much area? Just message 13 to 30. Yeah, correct. Because we downloaded SRTM data, which was 30 meter of resolution. So one pixel is representing 30 by 30 meter. So this particular pixel is representing a 30 by 30 meter area. Okay. Okay. So yeah. So if this particular pixel is representing 30 by 30 meter area of this area on the real world. Okay, so you can see, and each pixel will be having only one value. So only one elevation value it is going to have. Okay. So I hope this is clear. Now you can see, visualize the raster images and what are the different processing that you can do. And always keep in mind that we should reproject the raster in a um, like coordinate system which has units of meters. So projected coordinate system, not the geographic one. And this always check that if the projection reprojection has been done correctly or not. Okay. So this is what I wanted to tell you through this exercise. Okay. So you can also make contours, and there are lots of things that you can do. Okay, so we'll move on to the next part. There is another way of representation. So you have to tell me which surface representation use irregular triangles based on terrain variation: raster, tin, quadri, or polygon mesh. It is going to be tin. So tin is triangulated irregular network. So it use triangles to represent any surface. Okay. So this is how it is going to look. Okay. So it has some nodes. So these nodes are the points for which we know the data, and these edges are the lines connecting the nodes, and from this we get a triangle which is formed by connecting three nodes. Okay, so based on the elevation, a particular node is going to uh, like be close to us, so it will represent higher values. Okay, so this is how triangulated irregular network um, looks like, and it captures terrain very well, and but it is very hard to compare it with other layers. Okay, so mostly we use raster data sets only to represent the surface. Okay, so now you have to tell me, contour lines that are close together indicate what? Flat terrain, steep slope, same elevation everywhere, or poor data quality. So if contour lines are very close to each other, what is it representing? Yeah, correct. So this is representing steep slope. So if you remember our data, satin and contour lines. So if you remember, this is the mountain area, right? So here we have some, this is going to be uh, having steep slope as compared to this flat terrain, and you can see the contour lines are very close. Okay, so if the contour lines are close, it will represent a steep slope. So close spacing means rapid change in elevation. Okay. So I hope this is clear. So isolines. So this is what we have done. So it will be easy for you to connect to each and every point. So isolines or contours are lines that join points of equal value. So suppose for our case we used elevation. So what are the characteristics? It will form a closed loop, and the spacing between the lines can tell about the steepness, and cross ridges or valleys are at right angle. Okay, and this is very good for visualization, but without conversion the digital analysis is very poor. Okay, so now you have to tell me what 2.5D means. This term, flat map with shading, two horizontal coordinates plus one vertical value, 3D animation, or two projections stored in one file. Okay, so yes, 2.5D means two horizontal coordinate plus one vertical value. So this is used to represent terrain model like DTM or DSM. So this is like 2D, 3D. So this is in between 2D and 3D. This is 2.5D. Okay, and this is basically used in terrain models. Okay, so two horizontal coordinate plus one vertical value. Now, which factor does not affect the surface model accuracy? So what is the factor? Terrain variation, point density, interpolation method, or file format name? Which is not going to affect the model accuracy? Yes. So it is going to be the file format name. So whatever the file name is, it doesn't depend on that. So it was kind of obvious. So time in GIS can be represented as, so I already gave you the answer. So it will be attribute linked to the feature. Okay. So you can, in GIS you can represent the spatial features because the lat long values are in there in the canvas, but for the time it should be stored in the attribute table. Okay, so now we'll move on to accuracy factors. So there are different factors: terrain variation, measurement point density, distance between points. Then if you are representing time incorrectly, that can also lead to error. Interpolation method. Sorry, this is different. I should have tried to this. Okay. So sorry for that. So these are the points which give accuracy, and if you want to represent time it should be an attribute. Okay, Models for movable objects. So movable objects are very hard to represent. So it can be represented by a network model. So network model basically uh, gives like connected links or nodes, but the movement is restricted to that connected link. And for the surface movement model, movement can be done across terrain, like for example water flow. So for water flow direction, you can calculate the slope, or you can calculate the elevation, and water will always move from how like higher values to lower values. It will never go from like lower values to higher values. So that is how you can like make surface movement models, or how the water is flowing, that kind of models you can make. So which model is best for simulating car movement along the road? Surface movement model, network model, field model, or raster model? So this is going to be network model. Okay. So because the movement is going to be restricted or linked to link nodes or edges. So always the car movement is going to follow the road. Okay. So the road, or the line vector for the road, as you can say. Okay. Now this is what scale is. So if a map has a scale of 1 is to 50,000, that means 5 centimeter on the map is representing how much kilometer on the ground? Can anybody tell? Okay, Coil is saying 5 kilometers. So let's see. So this is going to be 5 into 50,000. So that is going to be 2.5 kilometers. At 5 kilometers. So always you have to multiply. So this one, so I'll just show you how can you do the calculation. So it is 1 is to 50,000. So sorry for this. I don't know why this happens. So this is 50,000. Assume it to be 50,000. So scale means 1 centimeter on the map is 50,000 centimeter on the ground. Okay. So if it is 5 centimeter, suppose this is 5 centimeter, then we have to get the value of x. So what will be the x? X is going to be 5 into, so this one basically 5 into 50,000. So this is going to be 2.5 centimeter. So scale is basically telling you the ratio. So if like 1 centimeter on the map, so that means 1 centimeter on the map will represent 50,000 centimeter on the ground. Okay. So now you have to tell me which of the following best describe attribute query in GIS. So in the first class itself, we talked about query. So I gave an example of query in the first class. So let's see if somebody remembers from that. So extracting feature based on their spatial location. B is extracting features based on attribute values. C is overlaying multiple layers. And D is georeferencing. So which one? we are talking about attribute query. Yeah, so Koel is correct. It is extracting feature based on attribute values. Now, which query type is used to select features based on their geometric relationship? So, attribute query, spatial query, geocoding, or raster classification? Yes. So it will be spatial query because spatial query is related to spatial data. So based on the geometric relationship, it can extract the data whether a feature intersects with something or it contains within something. So that relationship is used for spatial querying. Okay. So now we'll look in detail what querying is. So, querying is basically how you ask questions of spatial data to pull out just the feature you need. Okay, so querying is basically filtering data either by attributes or by spatial relationship. Okay, so suppose the question is what is example owner of a land parcel. So for that you need to know. This is a attribute query type. Suppose a parcel is within 2000 meters square. So this is spatial query. And predictive modeling is basically modeling or simulation. So I should have removed this. So what if is predictive modeling. So there are different questions type and we use different. So predictive is you are going to project it for future or you are going to like use existing information to derive something else. So that particular type of modeling is called as predictive modeling. So it is not based on what we have. We use some things to derive some information and then that type of modeling is called as predictive modeling. So for example, like based on the rainfall pattern for a particular area, we can make a model and say that these are the things on which the rainfall is dependent and this is how this is, or based on rainfall you can see this is how this rainfall is changing. So if this pattern continues, then this is what will happen. So here we are kind of assuming a few things, but in these two inquiring you have all the information that you need. For this modeling you have to assume a few things. Okay. Now, what are the types of querying? So, attribute query. So, it select feature by values in their attribute table. So, for attribute query, you just look at the attribute table. Then we have spatial querying. So for spatial querying, we select feature by their geometric relationship. So for this, we look at the, for example, you can see what are the, so if you want to get what are the areas which are very prone to a river flooding, so what you will do? So suppose this is a river is flowing and you want to know what is the area which is very much prone to uh, uh, like get affected by the floods from the river. So you can create a buffer around this, right? And you can say that whatever is like within 10-kilometer range of the river, it is going to get flooded. So this type of querying is spatial query. Then there can also be combined querying like attribute plus spatial. So for example, you will look at the school names and the schools that are within flooded zones. So suppose there are some schools here, here also, here. So for the first part, for getting the schools, you have to look at the attributes, right? And once you look at the attributes, after that, you also have to get an intersection that if it is a school, whether it is within 10 kilometer zone of a river or not. Okay, so this is a combined query. Okay. So, one example that I gave was that suppose you want to eat somewhere and you are hungry. And what you will do, you will try to find any restaurant that is within 5 kilometer of your area. So, what you will do? You will do spatial querying. So, suppose this is where you are. So, you will look at area which is within 5 kilometer within your, so you can reach there. Okay, now if you are vegetarian, you also have to look at the attribute that the restaurant should be vegetarian. Okay, so this, like looking at a vegetarian hospital, sorry, restaurant, vegetarian restaurant is going to be a combined query. Okay, so you have to look for some restaurant that is within 5 kilometer but also is a vegetarian restaurant. Okay, so this is combined query. So this is very simple. It is like data filtering based on like what we need. Okay, so for this, these are the different types. So you can select cities which have population of which is greater than 5 lakhs. Now, schools, the name start with cent, then land use should be residential. So these are like this, for this, it will rely on attribute table. Okay. So this is how attribute table looks like. So So can anybody tell what like which cities or how many cities are going to get selected if we use this attribute query where population is this is 50,000. So this particular greater than 50,000. So this will get selected, right? This one will not get selected. It is less than 50,000. This will get selected. This will also get selected. This also, this. Okay. So there like seven of them. So yeah, seven of them are going to get selected because they have population greater than 50,000. Okay. So now what is SQL? SQL is structured query language. So this is a standardized programming language that is used to communicate with the database. So in your QGIS, you have to use this structured query language. So this particular uh, format is structured query language, and using this you can get or filter those informations. Okay, so these are the steps that you have to do. So if you want to do make any attribute query, first of all, for in ArcGIS, you have to go to attribute table, then select by attribute, and then SQL expression is going to be population greater than this. Okay, and for QGIS also it is similar to this. You have to right click on the layer, then open the attribute table, and then select the features. Okay. So let's see. Right now we don't have, suppose here for the contours, maybe we can check. So first of all, right click and then go to open attribute table. So now if you open the attribute table, you can see we have FID, then ID, and then elevation. Okay. So suppose you want to uh, select the data or select the contours which have elevation greater than 500, or yeah, greater than 500. Okay. So for that, what we have to do, we have to open the attribute table and then select the feature using expression. Yes. So this is the icon, select feature using an expression. Okay. So now what we will do, type expressions, example population growth. Okay. So what we have elevation. Okay. So these are the different things, aggregate, array. If you look at the variables, we have geometry, ID, feature. So we can just type in, so elevation greater than 500. Okay. So now if you see here the variable feature, so now you can see these, all the lines which are greater than 500 are now highlighted in this color, yellow color. Okay, so you can see this is working, right? So this is how you can select by attribute. So this is what attribute querying is, and this is how you can do this. So when you apply, the matching features are going to get highlighted. Now next is which SQL-like command is valid in QGIS attribute query. So it is going to be first one. Okay. So select from cities where population is greater than this. So which query would you use to identify all schools names St. Xavier's in a city GIS database? What will you use? Anyone? It will be attribute query. Okay. Now spatial querying. Spatial querying is basically using relationships like intersection, within, contains, touches. We try to get spatial information. Okay. So for example, if you want to know villages within flood zone, so you can make a flood zone area and then see how many villages are there. So you can see there is one village within the flood zone area. So this is how spatial querying works. And for this, I'll In the next class, I'll tell you how can you do spatial querying in both QGIS and ArcGIS, and we will also explore how can we um, make buffer zones. So for spatial querying, making buffer is very important. So we'll show you how can you make buffer zone around a point or around a line. Okay, so these things are going to be done in the next class. So meanwhile, if anybody has any doubts, please ask me anything from any lecture. Okay, so no doubts. I hope everything was clear. Okay, then we can end this session if you have no doubts. Okay, so thank you everyone and happy Independence Day. And today the class strength is low, I think because of that only. So, yeah, happy learning and bye bye.